Hey guys, I am Gautam from IIT Kharagpur and welcome to GChemix. In this video, I am going to talk about equivalent and non-equivalent protons that are important to determine the structure or the number of peaks of a particular chemical compound or any molecules. Okay, so to determine the number of peak, that is important for every kind of examinations and of course of your studying also. Okay, so what will be the number of peaks in any compound or any molecules? That can be determined by the help of equivalent and non-equivalent protons. Okay, so the number of equivalent and non-equivalent protons can be determined by considering two things. One is chemical shift, another is magnetic equivalency or non-equivalency. And first is chemical shift equivalency or non-equivalency. Okay, so in this video I will be discussing these two, and let's talk about the first one, that is chemical shift equivalency or non-equivalency. So what is actually this, or what is this kind of equivalency? So basically equivalency means the nuclei. Here the nuclei means of course as we are discussing the PMR spectroscopy, so the nuclei will be protons, and the protons which will have the chemical shift, same chemical shift or equivalent chemical shift. Suppose in a system there are 2 or 3 protons, and those protons will have the same chemical shift value, or if those protons have the same chemical shift value, then we will say that the protons are chemical shift equivalency. Okay, and if those protons will not have the same chemical shift value, then we will say that those protons are chemically non-equivalent. Okay, so let's talk about different kind of operations or different kind of things that we may apply to determine whether two protons will be chemical shift equivalent or not. Okay, so first let's discuss the chemical shift equivalency, and the points are number of CN axis, that is you have to find the axis of symmetry, then the sigma plane and or I. So the number of axis of symmetry, sigma plane and inversion center. So if a system present any of these kind of things, then we can easily determine whether the protons are chemically equivalent or not. Okay, so let's take an example regarding CN. So say this is the example. So you know this is actually tetrahedral structure. This bond actually will be below, or this will be above like this, but I am drawing like this. So you know about this, that the structure is tetrahedral structure. This has a tetrahedral structure, and that is why if we will apply C3 axis of symmetry over here, then we will get the same structure, same 3 structure. Okay, so suppose this is HA, this is HB, and this is HC. We are representing the hydrogen atoms with HA, HB and HC. So HA, if we rotate first, then HA will go to HB near here, and HB will go right here, and HC will be right here. Okay, so here these hydrogens can interchange their positions by applying the C3 axis. Okay, so that is why, and overall symmetry of the molecule is quite same before and after rotation. That is why HA, HB and HC, we will say that by the operation of C3, HA, HB and HC are chemically equivalent. Okay, so that is why after rotation, that is we are applying CN, and we will get the 3 protons that are chemically equivalent. Okay, so that is why we will say that the chemical shift equivalency is present right here. Okay, so next talk about, say, another example like this. This is Cl, this is Cl, this is below, this is above bond, there is another 2 hydrogens right here. So here also you can find, I am just giving example on CN. Okay, so next I will be discussing sigma and I. So here also C2 axis of symmetry is present. How because this is above, this is below, and these two hydrogens are on the same plane of the board. Or that is why if we rotate like this, C2 rotation we apply here, then we will get the same structure. So here we will just consider hydrogen atom, not the chlorine. So HA, HB, suppose we are representing like this, and then we will see that after rotation, C2 rotation, HB will be right here and H will go right there. Okay, but the overall structure of the molecule will be quite same. Okay, and that is why after interchanging their positions, the overall symmetry of the molecule or overall structure of the molecule doesn't change. That is why this system or these two hydrogens will be chemically equivalent. Okay, so I will be discussing the non-equivalency after showing the equivalency. Okay, so I have shown you that by applying the Cn we can easily determine the chemical equivalency. So now let's apply the sigma, that is sigma plane or inversion center. Okay, so let's take an example like this. This is CO2H, this is C, sorry, let's take this one as below bond. This is CH3, this is H, this is another H. Okay, so now let's represent this as HA and HB. So if you can apply a sigma plane from here, and this will be towards the above, this will be towards the below, so you have to consider this like this way. So this is above CH-methyl and this is below C-double-H group, so this will be on this plane. Okay, this is sigma plane. Okay, and this two will be towards this way and this way. So this HA and HB will be the mirror image of one another. Okay, so as these two are mirror image, so these two H and HB will be equivalent. Okay, so let's take another example so that you can easily understand this one very clearly. Okay, so the next example will be like this. Say this kind of system is present here also, here C, here another above group, that is say chlorine, fluorine, hydrogen, another hydrogen. Okay, so these two hydrogens, that is HS and HB, will be equivalent because we can apply sigma plane from here. That will be like this, and that this will be towards the above and towards the below, and these two will be on the same sigma plane. Okay, so by applying this kind of sigma plane, we can see that this HA and HB will be the mirror image of this sigma plane. Okay, or if we apply one mirror right here, then HB and HA will be equivalent because we will get the mirror same atom after applying the mirror, because HB will go right here and HA will come right here. Okay, so this HA and HB will be same or equivalent, we may say, and that is why HA and HB, here HA and HB, here HA and HB, and here also HA, HB, HC, all are chemically equivalent. Okay, so I hope you can understand what is chemical equivalent by applying Cn sigma. Now coming to I, and how inversion center can be applied right here to check whether a system is chemically equivalent or a system's hydrogen is chemically equivalent or not. Okay, so let's take an example like this. This may be a complicated example, but you can easily understand what I am trying to say. So say here, so here you can see that HA, and you know of course that I, how inversion center is present in a system, so it will be like right here, and if we go towards the above, towards this direction, and we will find fluorine atom, so you have to go towards the opposite direction, and we same here we will get another fluorine atom. And similarly chlorine, this chlorine and this chlorine are corresponding to this I, and also HA, that is towards this direction, towards the above of the plane of this plane, and this is towards the above, and this HC, that is HA and HC, are, you may say, inverted with respect to this point. And similarly HD and HB will be present towards the opposite direction of this point. Okay, So that is why this point we will say inversion point or inversion center. Okay, and that causes that results the HA and HC will be chemically equivalent, and HB and HD will be chemically equivalent. Okay, because this center represents this and this as you may say, or this hydrogen and this hydrogen causes this center as inversion center. So I have already said you that CN axis, sigma plane or I, if these kind of things are present in a system, then these things, these rotations, these axis of rotations of sigma plane or inversion center, these will be responsible for the for creating the chemical equivalency. Okay, so now coming to chemically non-equivalency. So what is chemically non-equivalency? So this will be opposite of this one, whatever I have told you. Okay, so if in a system there is no plane, so that we can determine two protons or two different protons as chemically equivalent, then we will say that these two protons will not be chemically equivalent. So let's take an example. Say I am considering common example. Suppose this OH, this is CH3, this is hydrogen. Another point, that is hydrogen, this is another hydrogen, and this is C double I's. So you know this center is chiral center, and you cannot rotate, you cannot apply any rotational axis or any sigma plane over here, because these four groups are different. Okay, so here these two hydrogens, that is H, these hydrogen and these hydrogen, we can verify whether these two are chemically equivalent or not. So after any rotation, you cannot find these two hydrogen can interchange their positions, because if they interchange their position, then this system will also interchange their position, but these all the groups are different because this center is a chiral center. Okay, and because of this, these two hydrogens we cannot change their position, and that causes the system as chemically non-equivalent. Okay, so because there is no Cn or sigma or I, no Cn, sigma or I is present in the system. Okay, and that is why these two hydrogens will be chemically non-equivalent. Okay, so this is a chiral system. They may ask a question that give an example, or in any question, just you should remember this, that so this is the chiral molecule that has no chemically equivalent protons. Okay, so now coming to next example, that is quite the opposite one, but also these also have no chemical equivalent protons. So this is a achiral molecule, but also this has no chemical equivalent protons. So the system will be like this. Okay, so this system will be, here you can apply the sigma plane, because this sigma plane will be like this, and this is OH is above and this H is towards the below side, and that is why this OH and this H will be towards on this plane, this sigma plane, and that is why this and this will be of course a sigma plane is present in the system, and that causes the system this makes the system achiral. Okay, or the molecule will be achiral, although this has the sigma plane, but two protons, that is we may consider this one and this one. Okay, these two proton will not show, or this one will not show any kind of chemical equivalency, because you cannot this is below, this is above, this is above, this is below, so you cannot rotate the system. So if you rotate the system, then this say this is HA, this is HB, this is HC, and this is HD. Okay, HA, HB, and also HC and HB. So these two and these two will be diisotropic. Okay, and because of this are diisotropic, so these systems will not be chemically equivalent. Okay, so just find this kind of system. Okay, then you can easily determine the system, whether the system is chemically equivalent or non-equivalent. So now coming to another example, also of course by the regarding the chemical equivalency or non-equivalency, but it's quite different. Okay, so first let me clear the board, and then I will show you. Now I am to show you some one important thing about the chemical equivalency, okay, or non-equivalency. Let's take an example. That system shows both chemical equivalency and chemical non-equivalency at different conditions. Now let me take an example, and in that example I will show you a system that will show both chemical equivalency and non-equivalency. Okay, say the system is like this. Okay, so in this system, proton means basically these methyl proton and these methyl proton may show different kind of chemical shift value. Of course these proton also show, but we are considering these two kind of methyl protons. Here you can ask one question, that this methyl and this methyl, can these two systems show any kind of chemical shift equivalency, or these will show the non-equivalency. Okay, so I will consider two things. At first is room temperature, second is high temperature. So what happens at room temperature? So at room temperature or at normal temperature or biological temperature, this kind of resonance easily occurs. Okay, and that gives the system like this. Sorry, this will be N CHT, and these CHT, that is these protons, will interact with this hydrogen, and these protons will interact with this oxygen. So interaction will be different, and that causes these two methyl systems non-equivalent. Okay, because here no any kind of sigma plane or axis of symmetry or inverse center is present. Okay, so here non-equivalency, but one thing is, at high temperature what happens, this kind of resonance, the rate of this resonance occurs very fast. Okay, because of this double bond character and single bond character are nearly at equilibrium, and that causes this system totally the maybe single bond or double bond character. Okay, or you can say it is single bond, or you can say it is double bond, because the conversion occurs very rapidly. That causes, say this behaves like a single bond, then this bond easily rotate. Okay, so this methyl can go towards right here, and this methyl will come like here. Okay, in the position of this methyl, and that causes these two methyl chemically equivalent. So at high temperature this system is chemically equivalent, at low temperature this is chemically non-equivalent. Similar case you can see in keto-enol tautomerism. So what happens here? So at low temperature the enol form is stabilized, but at high temperature the conversion of keto and enol form changes. Okay, or it is very rapid, and that causes the interconversion between the keto and enol form very fast. Okay, so that is why at high temperature that is in the keto and enol form, the hydrogen near the keto group may behave like chemical equivalent, but at low temperature it behaves like non-equivalent. Okay, so this kind of things you can face in different kind of examinations. Okay, so the systems like this show both chemical shift equivalency and non-equivalency depending upon the temperature. Okay, I want to add another example right here, because this is very important. Say this is HA and this is HB, and after flipping, system will be like this, and this will be HB and this is HA. Okay, so the system behave like this, that at room temperature or at two temperature, room temperature and low temperature. So here room temperature is, we have to consider high, and low temperature will be very low. So at room temperature what happens, this interconversion is so rapid that the axial and equatorial, so here HB will axial position, so here it will be equatorial position. Okay, so that is why here axial and here equatorial, this interconversion will be so rapid. Okay, at room temperature, but at low temperature interconversion rate will be slow, and that causes these two non-equivalent. But at high temperature, as this changes, this HB changes its position in here HA, near HA, and HA also changes its position to right here. Okay, and that causes HA and HB chemically equivalent, but HBA and HB at low temperature, as the interconversion is rate of interconversion is low, so these two are not chemically equivalent. But at high temperature or room temperature, it is chemically equivalent. Okay, so this is all about the chemical shift equivalency and non-equivalency. So now coming to magnetic equivalent, and it is also called spin coupling equivalent. Okay, so let's take different kind of one example I want to show you, that will be enough to prove that the system, which is what is actually magnetically equivalent, what is or chemical spin coupling equivalent. Okay, and why, how it is different from chemical equivalency. Okay, so let's take an example like this. So just try to understand, because it's not that much easy like chemical shift equivalency. So here this I am considering a benzene ring. So say here N2 and here is Cl, and 4 different hydrogens are present. So why I am telling 4 different hydrogens, because say this is HX, this is HA, this is HA prime, this is HX prime. So HX and HX prime are near the NO2 group, so these two will be chemically equivalent. So HX and HX prime chemically equivalent. Okay, CE, HA and HA prime near the Cl atom, so HA prime also chemically equivalent, as both are near the Cl atom ortho position. Okay, but suppose, what is magnetical equivalence? Magnetical equivalent means HX interacts with HA prime and HX also interact with X prime. So these two interaction may or may not be same. So what do you think? Because here is NO2 group, here is Cl group. Okay, so you can easily understand these two are not same. Okay, but HX and HA, or HX prime or HA prime, these two are not chemically equivalent. Although these are equivalent, these and these equivalent, these are two chemically equivalent, but HX and HA or HX prime or HA prime are not chemically equivalent, because this corresponds to Cl, this corresponds to NO2, near the nearest groups. Okay, so these will affect on this system differently, and also this will affect differently. Okay, so that is why these two are not chemically equivalent. So what is magnetically equivalent? Magnetically equivalent means, suppose these two should be magnetically equivalent. So to be magnetically equivalent, first these two have to be chemically equivalent. Okay, so the condition is, to be magnetically equivalent, this system also should be chemically equivalent. Okay, but to be chemically equivalent, the system need not to be magnetically equivalent. Okay, so if these two protons need to be magnetically equivalent, then these two protons first need to be chemically equivalent. Okay, as these two are not chemically equivalent, so we can say that these two will not be magnetically equivalent. This is first condition. Okay, so first condition is, to be magnetically equivalent, this is the two protons should be chemically equivalent. Okay, and the second condition is, to be magnetically equivalent, suppose we are considering these and these protons. Okay, so except these two protons, we are considering these protons, so we just want to check this proton and this proton are either magnetically equivalent or not. Okay, so we just need to consider another proton, suppose this one or this one, so whatever you may consider. So I am considering suppose this one. So these and this, the interaction between these and this should be similar, the interaction between this and this, but the atmosphere of these two proton, this proton and this proton, is not equal like atmosphere between this proton and this proton, because chlorine, because NO2 chlorine. So okay, so you can different atmospheres these two protons belongs to. Okay, and that causes these two magnetically non-equivalent. So first condition should be chemically equivalent. Second condition is, this proton will be similar interaction with this, and also this proton have to have similar interaction with this. Okay, then if they have similar interactions, then these two will be magnetically equivalent. So the line is, magnetically equivalent protons are also chemically equivalent. So remember this line. you may face a question, true false question on this. Magnetically equivalent protons are also chemically equivalent, but reverse is not true. That is, chemically equivalent protons may or may not be magnetically equivalent. Okay, so remember the line. Okay, so this is all about the basic equivalency and non-equivalency, that is chemical equivalency and magnetic equivalency, or spin coupling equivalency or non-equivalency. Okay, so this is important for the for finding the number of peaks you will get for a particular molecule, say this kind of molecule. So first you have to understand the chemical equivalency or non-equivalency, and then you can easily find the number of peaks you will get. What will be the number of peaks, how many peaks you will get from a particular molecule or a particular compound. Okay, and I will discuss that topic in my next video, and that will you get tomorrow. Okay, so however, just I hope you can understand this one, and if you have any query, then you can comment below, and in the next video you will get how to determine the number of peaks you will get for a particular molecule via NMR spectroscopy, and further you will get the structure elucidation, okay, by IR and NMR data. Okay, and this is very important for different kind of examinations and also for your general study. Okay, so whatever, that's all about today's list. So keep following, keep watching, and thanks for watching.